thank you for coming to this presentation. Today I'm going to talk about PGTracer, which is an open source tracing tool for Postgres. The idea, as I will explain, is to use Linux kernel facilities to perform tracing on a running backend, and the idea is to not touch anything to your Postgres configuration to be able to gather information about what's running on it. So a few words about myself. I'm Ronan Dunklau. I'm an open source developer at Ivan. Ivan, what do we do? We're the trusted open source data platform for everyone, which means you can use us to deploy Postgres services in the cloud, but also Kafka, OpenSearch, and if it's open source and you want to deploy it to the cloud, chances are we can do it for you. So I was formerly a DBA, and I've been working in the Postgres ecosystem for the past 10 years. I've been worked on things like GQual stats that Lukasz mentioned earlier, and things like this. So to better understand the use case for a tool like PGTracer, I want to start with a quick survey. If everybody is awake enough to raise hands and answer questions. So how many of you have used pgstat statements? Almost the whole room. That's about expected, but yeah. So for those who don't know, pgstat statements is an extension which is packaged as a contrib to Postgres. So it has a similar release life cycle as Postgres itself. And it's really great because it allows you to gather information about the workload on your database. So you enable it, and then you will be able to see cumulative counters about what's happening on your backend, like those queries are taking this time on average. They can take up to that time. They have been executed this number of times, and so on and so on. So it's really great, but it gives you information about your whole workload. You can't know what a specific backend is doing, or a specific query execution did it take too long, or why, and things like that. So for this, we have other tools. How many of you have tweaked log min duration statement? And by that question, I guess my real question is how many of you have used pgbadger or something like this? Yeah, because in the log file, by turning log min duration statement to 0, we can ask Postgres to log every single query, and then we can use another tool like pgbadger to generate pretty reports from that. And that really helps us to answer the question, why was this query, what was this backend doing, and what query was it executing, and we can see the duration it took and things like that. But this requires being a bit, you need to think about it in advance. When you currently have some problem on your server, it's usually not the best of time to start messing with configuration parameter, and also it has quite a bit of an overhead because you will start logging lots of things, and you can target things by user and or DB specific settings, but you can't really turn it on only for a backend. So that's really good, but it doesn't really help us solve the problem of what is this specific backend doing right now. In addition to that, we also have auto-explain. Auto-explain works a bit, it's the same concept as tuning log min duration statement. We will just ask Postgres to log lots of things. So how many of you have used auto-explain? Yeah. So basically the idea is that we ask Postgres to log every single execution plan if the query took more than a certain amount of time. And it's really interesting because then you can collect the plans of your slowest queries. But as always, that requires you to think in advance that you're going to have trouble, and you can't really enable it on a specific backend. So these tools are really great, but they don't solve the problem of I have something going wrong right now, and I want to try to understand it without modifying the whole system. And for this, we have another tool, LinuxPerf, which is not Postgres specific, but I'm sure some of us have used it. Please raise your hands. LinuxPerf. Yeah. So LinuxPerf is really great because you can just run perf on your system. It can do many, many different things and collect lots of information, but one common use case for it is to just gather sampling of the execution happening on your system and then trying to figure out where your system is spending its time. So for example, you can see precisely which C functions are responsible for the most busyness on your system. And that's really great. But the thing is, that's not that good for Postgres developers, because thinking about C stacks and functions and stuff like that really helps. But for a DBA, that doesn't really correlate with what you think about when you think about performance problem on your database. So what if we could have some tool which would basically do a mapping between a system view of things, like a call stack like perf, and an execution plan? So the idea is to have tools a bit similar to perf to gather information about a running process, but in Postgres terms and not in generic programming terms. So, feature request. So one thing that would be great to have would be to have the equivalent of being able to log every single query from a backend, like a log min duration statement, but enable it for a specific backend and see precisely in real time what is happening. That's, in my opinion, a desirable feature. Second thing is we could also have a tool which would be able to turn on instrumentation on a running backend, just like auto-explain does, and force Postgres to gather additional information about your queries at the price of small performance degradation, but something that can enable you to understand what is really happening. And much, much more, because we also want to be able to gather a live execution plan for our running queries. That could be a nice thing to have to understand what is happening in real time. And once you start going through this rabbit hole, you have lots of ideas about things we can do. So to take a step back, so PGTracer's use case, the main use case is that a backend is misbehaving and you want to investigate right now in real time what it's doing. And you don't want to have to spend a lot of thought about enabling things and configuring things and adding overhead when you're not using it. So this is a list of planned features. Most of them have been implemented. So we want to be able to dump queries live. We want to be able to reconstruct execution plans from the running query by poking at the running process. We want to be able to extract instrumentation information, the same one that explain, analyze, gather. And if we are not constrained by having a tool running in Postgres itself, we're actually not limited to Postgres. We can also look at the whole stack, because Postgres does a lot of things by itself, but it still relies, for example, on the libc to perform memory allocation and things like that. It relies on the kernel to actually read data or write data to your devices. So this can allow us to have a more integrated approach over the whole system that Postgres uses, and not only Postgres code. One thing that has not been implemented now, but which is a desirable feature, would be to also be able to follow transaction boundaries and then say that we want to have normalized transactions. The same way PGStat statements normalize queries, it could be interesting to also normalize transaction and know that we have a typical transaction is, well, I select a customer and then I update it. That's some pretty typical transaction that lots of systems are going to encounter, but being able to group not only by queries, but by transactions also gives you a better idea of what is happening in your system. Because usually an application will have a small number of typical transactions that they will be running. I will perform a demo later, but as of now, PGTracer is mainly one tool, one script, PGTrace queries. So how do you use it? You give it a PID. It can be either the PID of a specific backend, that's the most common use case, but recently we also added support to trace the whole Postgres cluster and gather information on all running backends. And you can pass it a bunch of options to turn on instrumentation and things like that. So what it will do is it will start loading debug symbol. It will attach EBPF code. I will get back to it in a while. And then as it's running, it will dump on the console everything that is happening in this backend. So for example, once this has been running, the Postgres backend with PID 7642 has been running this query, select star from PG class, and we can see a list of what is gathered by PGTracer inside this process. So we can know that this query had a runtime of 2 milliseconds. It was run with a specific search path. Somebody mentioned earlier that quite often that's information we are missing, some specific GUG values, and especially important one like your search path to know exactly which tables your query are run against if you have several schemas with similar table names. And then we have information, the instrumentation information, like the buffer usage, how many blocks we've hit, we've read from the shared buffers itself, how many blocks we've asked the system to read from us. And we can also correlate that with syscalls performed by Postgres at the same time. As I mentioned, since we are not constrained to Postgres itself, we can also instrument the Linux kernel, and then we can get an approximate ID. Well, this is quite approximate because we are only looking into the I/O performed by the same process we're in, but we can still get an idea of what was served by the Linux kernel file system cache and what was actually sent to the device. So the idea is, how does this work? If we are not in Postgres, how can we extract that information? So it's based on EBPF and debug symbols. How many of you know about EBPF? Have already used it or just heard about it? Okay, so EBPF stands for Extended Berkeley Packet Filtering, and it's a Linux kernel facility. So basically, at first, I think it started as a way to write firewall and networking utilities because, well, that's the name, filtering. But eventually, over time, it has grown into something much more interesting. So we have several types of EBPF programs that we can run. The idea is that we write an EBPF program. Usually we write it in something that looks like C. And then this thing is compiled to EBPF bytecode, which we can load in the kernel. And the kernel will run a verifier on this to make sure that we don't run anything dangerous. For example, since this will be executed inside the kernel, we don't want to allow unbounded loops. We don't want a program that could just run forever in the kernel and never give control back to user space and things like this. So what we do in PGTracer, we install trace points. Well, I say trace points, but technically it's trace points. It's user-defined dynamic probes, user-defined static probes, and things like that. But let's just say a trace points, and we install trace points as specific function calls. For example, every time the executor starts, we have a trace point here, and this will trigger some code to be executed in the kernel. And this code will do things. It will gather information from inside the process. Same thing with executor finish, with portal drop. Basically, your whole query lifecycle will be instrumented at several points. Some code will be executed, and then PGTracer can do something out of it. So, for example, this is a small sample of EBPF code. It looks a lot like C, because it's some sort of C frontend, but it's actually not C, because it gets compiled to EBPF bytecode in the end, and not to machine code. So the idea is that every time we will attach this function to be run every time the portal drop return is executed in Postgres itself, and we make use of the EBPF provided facilities like the ring buffer. So EBPF provides us with several data types that are managed inside the kernel. Like we have hash tables, we have things like this, and we can use this to store information and send it so that a program in user space can read it and do something about it. So the general workflow is that we attach code. This code will be run every time a specific function inside Postgres will be run. And then this code will send data using a ring buffer. It will send data that can be exploited by the tool in the user space. So what can we try to send from this code? So we're trying to gather instrumentation data. For example, how many buffers did this query read? We want to gather the query text. We want to gather, for example, some gugs. I've showed the search path, but maybe we are interested also in dumping the workname setting for when this query was running and things like that. And the thing is, we can also, with EBPF, we can not only read any memory in the program, in the user space program, but we can also write to it. That sounds scary. It is. And the Linux kernel will tell you about it whenever you load an EBPF program that has some function calls to write memory. It will dump a warning message in the kernel logs telling you that maybe this thing is dangerous. But it's really practical because then you can inject code to modify the running process in a safe-ish way, in a way. If, for example, the main way we use this in PGTracer is to enable instrumentation. So when the query, before the query starts, we override the return value of a function to add new flags to turn on instrumentation. And that allows us to modify the behavior of the trace process without touching Postgres at all from inside. We don't have to compile an extension, we don't have to change a setting, we don't have to change anything. It's just a modification completely outside Postgres. So I mentioned the fact that we use trace points in PGTracer, but we also use those trace points to instrument what happened at the kernel level. For now, we just trace a block request issue trace points, which allows us to gather information about what type of block request it was it a read or write, how many bytes were asked, and then we can also send this back to user space. So to summarize, this is how it works. We have a user space program, PGTracer, which needs to be run as root because of limits on what you are allowed to do or not with the EBPF subsystem. So whenever you run this script, what it does, it will install an EBPF program into the Linux kernel, it will load it, and it will attach this program to different functions in Postgres, in the glibc, in the kernel itself. And whenever those functions are called, the EBPF code will be triggered. And this code, what it will do, it will send events through the ring buffer that the client program PGTracer can then consume and display things about. So you can see it as a publishing events architecture. Now, you may ask, well, I said that EBPF code is quite limited because there are lots of things you're not allowed to do with EBPF code. You have to prove that all your loops are bounded, your memory access, the verifier tries to prevent you from reading stupid memory location, and so there are lots of things you can't do, and also you're quite limited in the size of code you can actually load. So one thing we can't do, which would be really easy, since we have a C front end, maybe we could just include the Postgres header files, and then we know the structure of the memory inside the process, and we can access it like this. So, except we can't do this, because including the headers in a EBPF program is just not possible. There are lots of things in our headers that are not supported by EBPF. So we can't really do this. So what we do instead in PGTracer is that we use the dynamic access to memory. So basically what we do is from the debug information, we compute memory offsets from the base address of the program, and then we can access whatever we want. So for this, we use DWARF, which is the standard debugging format. So chances are you've already used DWARF without knowing. Anytime you run GDB, what it will do is it will use the debug symbols that are embedded either directly in your L file or a separate debug info file, but it will use this exact information to give you all you want to know about your program, to know that at this specific point you're inside this specific function, that the argument to this function is of this type and it contains those members, and so on and so on. This is all information that present in the DWARF debug information. In particular, one really simple example is to know the global variables locations. If you know that a global variable location resides at a certain offset from the base program address, then in EBPF code, you can just read exactly this memory address to get the setting you want. So that's really useful to get like GUCs and things like that. But also it allows us to have the complete types definitions and all the information needed to process functions and call stacks and so on and so on. A small example about DWARF. So this is the output from the library I'm using to parse DWARF information. And so just to give you an idea of how it works, here is the DWARF information for the instrumentation struct, which is defined in Postgres. And then starting from this base type, we can know that it has several members. And for every member, we can know its name, its type, and the offset from the base of the struct it resides at. Whoop. So for example, we can see that at this offset, we have a member named buff usage, and its type is a struct named buffer usage. And then we have the information outside in other information in the DWARF information. We can resolve this one and then access all the individual fields we want and know the amount of buffer from the shared buffers and which one was read and so on and so on. I saw a raised hand. No, this is a dump of the information in the DWARF information. And when it's field members, the location is relative to the start of the struct. So basically, it's telling you that if you have a variable of the instrumentation type at offset F8, you will find a member named buffer usage. And this is really useful because we don't need to get a header for every specific Postgres version. We get the information from the debug symbol, so whether we are running against Postgres 12 or Postgres 15, we don't really care. We have the debug symbols, and we know that the field will be at this location for this specific executable. So how do we use this information? So what we do is that using this information, we compute the specific memory offsets we need to read. For example, if we are instrumenting a function which is taking a node as its first argument, we know that from the debug information, we know that the node tag is right at the start of the struct. So we can read this information and send it to the client code. And then the user space code can read this memory and then parse it according to the debug symbols. If we read a whole struct, like a whole instrumentation struct, we will then be able, client-side, to split it into different fields and make sense of those different fields one by one. Okay, so I mentioned different things, how we can gather information about running queries and things like that. And also I mentioned that it would be nice to have explain plans and to basically collect information about not only the whole query, but individual node. This is something that other tools don't do, and well, for good reason. It's really expensive to instrument down to the individual node. But we can maybe try to extract some information about that. The thing is, as I mentioned, we can't embed too much code into EBPF. We can't have the knowledge in the EBPF code about every single plan node. So another problem is we don't want to attach to every single node execution. Because when you run, for example, if you run a sequential scan on a table with 1 million rows, you don't want to generate 1 million events because you just called this 1 million times. It would just be too expensive, and you won't. On one hand, it will slow down your execution to the point that there's no point in trying to understand what's going on anymore. And the other hand, you would generate too much data and you wouldn't be able to make sense of it. So what we do instead is we just attach to exec proc node first, at exec end node, so that whenever an executor node is started and then it's ended, we can gather some limited information about it. What we collect is its node type and its instrumentation, if that's been enabled. The next question then is, well, with that we can capture individual node information, and then we will have a big set of nodes, but we have no way of connecting them together to rebuild a tree. And that's where we use a clever trick, which is to collect the whole stack. We collect the individual node data, but also the whole stack at this point. What does this buy us? It buys us the ability to unwind the stack to find interesting functions. Remember what I said at the start about perf and about how perf gives you information in terms of code related to your stack call. But now maybe we can map this stack to individual function nodes. So that's what we do. So to give you an example, let's start with a really simple query like that. This query is just a select from one table joined with another one. And if you run that through explain analyze buffers, you can see a straightforward plan. We will perform a nested loop. This nested loop will perform a sequential scan on the inner side, and then perform an index-only scan for every row it found in the sec scan. So that's a really basic plan. So if we want to rebuild this information from outside Postgres, how do we do this? So what we do is that the executor will start, and we will encounter an execution of a node. So we capture the whole stack, and this is what we get. We have an argument and, well, with some pointer, and we can capture that this is a nested loop. From the EBPF code, we read the node type and its instrumentation data, and we send this to user space. So now in user space, we have a reference to a node, and we know that at some point a nested loop has been built. But then the execution continues, and we end up hitting another node. And for this other node, we also capture the whole stack. So this node is a sequential scan. So when residing here, and we send this back to user space, and by walking the stack, we can see that we have another function which is called with some pointer. And this pointer is the one we saw before. It's a nested loop we saw at the previous step. So basically what we are doing is we are mapping the SQL stack with the individual execution nodes. And by doing this over and over and over again, we end up with this. So if you look at this, it looks quite a bit like an explain plan. But it's not, because it's been generated completely outside of Postgres by just poking at Postgres memory and the stack. And as you can see, we are missing some important information, like we don't have the table name or the index name here. But still, we have the general shape of the plan and the instrumentation data for each node. And I think that's quite valuable information already. It would be possible to extract the OIDs for the scan objects and things like that, but that requires quite a bit of specific code for specific nodes. For now, this is purely generic and just work with the node types without giving any special behavior to any special node. One other thing that I will try to demo if I have the time, this is something that has been added after the fact, following a suggestion by Robert Haas. Since we're able to attach to the backend and we're able to write memory, why not have a utility to change the GUC of your running backend? So there is a utility with PGTracer which just allows you to do that. You can just attach to a backend and overwrite the current value for a global variable and then change the configuration. And why would you want to do this? Because sometimes you have a backend which is misbehaving and you would want to change its configuration and you can't really do that live. Some people have tried to use GDB for doing that, and usually, well, except if you're lucky, but it may end up really badly if GDB just stops your program execution right in the middle of wait for a lock or something. In this way, it allows you to attach behavior and change what is happening in a controlled way, because this is attached to a specific point in the execution of the Postgres program where we know it's safe to do so. So, small demo. Is it big enough, or do I need to? Yes. So on the left-hand side, what we have is a PSQL connection. So we get the backend PID because we want to trace this specific backend at the time. So, oh, that's a weird PID number. So we can run it and tell PGTracer to turn on instrumentation, and then we will see what happens. So first thing that PGTracer does is loading your debug symbol. It allows you to use, it can use a GDB index if there is one in the debug symbol file, but otherwise it will extract information in some sort of local cache to make symbol resolution speedier and things like that. Once that is done, it will compile an EBPF program specifically for your version of Postgres by injecting the offsets and all the information it found in the debug symbols and load that into the kernel. And once that's done, the client program can start listening to the ring buffer and start collecting events as they are produced. So if you take a really simple query, like select one, we will see it appearing here. So we will have the query itself, its search path, some information gathered from the planner itself, how many rows it is expected to return, the startup cost, total cost, and things like that. Then we have instrumentation data, its runtime, the buffer usage, wall usage, and some specific information that is coming from outside Postgres itself, like number of bytes that were actually written to disk, the hit ratio to the shared buffers by looking at what block requests were issued by our process. We can see what's happening in the kernel itself. And also we hook into glibc to try to get a sense of the peak memory allocation we have, because memory allocation in Postgres and in the glibc are two different things. And sometimes you may think you're using a certain amount of memory, but due to the way memory allocation works, you may be using more. So it allows you to see the peak memory allocation during this query too. It's mostly, as of now, it's mostly a way to demonstrate that we can do that kind of thing. But if we start having, well, I will restart it and ask it to collect individual nodes data. So now if we look quite a simple query. Ooh, I was not expecting that. But we still get the plan at the end. So the idea is that we've run, I don't know why there was an error before, but we still have the query itself, all the metrics we gathered about it, and this execution plan from the query we just ran here. So it is the actual execution plan that was used and not something gathered after the fact by rerunning explain with the query. It's the one that was already here. The interesting thing is that we can also gather information from a running query. We don't actually have to wait until it's over. And now we can see how the query is performing. that's a bit strange. No, I know why this happens, because this is quite a synthetic query, because using pgsleep, we are actually not doing much. We are mostly, well, sleeping. And the way this works is that by using perf events, so sampling, so we have to, there must be something happening so that we can gather information. But if we're running like this, we will see the sequential scan going over and over and have normally the number of rows used go up as we gather information. So yeah, that's about it. So I hope I showed you that we can gather information that is otherwise quite hard to gather. And you can do it for a specific backend, which is quite useful. Next, what could we do in Postgres to make that kind of thing easier? One thing would be to create more. We have a lot of static trace points in Postgres to be able to attach tracer and profiler to it. But having more static trace points would be nice, because we wouldn't have to rely on debug symbols as much, because if a static trace point is defined, it's easier to attach to it rather than having function signatures and things like that, which are not guaranteed to be as stable in the end, especially for things that are not really intended to be used by extensions and so on. Another thing, one thing I found a bit frustrating is it would be nice to have some more global state. For example, if you're in the middle of the glibc, it would be nice to have somewhere a global variable pointing to the current node being executed to be able to correlate what you see outside of Postgres to what is happening inside Postgres. Currently, we do this by capturing stack trace, but that's a bit much. By capturing the whole stack and then working it, that's pretty expensive to do on the client side. It's not really expensive in the tracing code itself, but then working the call stack is quite expensive and a bit hard to do. So if we could say that, well, right now we are executing this node, it would make things a lot easier to just correlate things together. Some few fun things I've found when working with eBPF. One thing is that we need to have cap sysadmin, because there is a cap eBPF capability, but it's mostly meant to be used in conjunction with cap netadmin when you want to stick to the base use case of eBPF of writing networking tools. But whenever you want to do tracing and when you want to do more advanced stuff, you need cap sysadmin to load your program into the Linux kernel. That's quite a limitation. Usually people like their tool to not have root writes. The eBPF verifier is a bit constraining. I mentioned how it prevents you from writing unbounded loops, and that's really great. But also it tries to prove that your value will stay within certain bounds. For example, when you're doing memory reading, memory access and things like that. And sometimes it just gets confused due to the way things are compiled. For example, if you have a bit too much register pressure, it will start storing your variables elsewhere, and then it will lose track of the bound of your variable. So if you write some code saying if x is less than 10, it can get confused then and say, well, maybe x can be max int. And so, yeah, it's a bit constraining to use, but once you get the hang of it, you're able to solve the problem as they go along. Also, using DWARF information is quite complicated, because the standard has been evolving, and the standard is evolving, but also the tools producing DWARF debug information are evolving too. So for example, we have lots of extension coming from GCC, some GNU specific extensions, which later become standardized, but then have a different meaning from the standard. And so you have to juggle with those kind of things when something changes from one version of the standard to another, and whether we use proprietary extensions or the standard itself. One of the things I'd like to add next would be, well, the thing I mentioned about following transaction boundaries and being able to extract typical transactions from a running system, but also being able to better relate things happening in Postgres to the outside world. For example, correlating palloc p3 with what happens actually inside glibc with what happened actually in the kernel itself, and have way of the whole integrated system of memory access and where do we get memory amplification and things like that. Same thing with I/O access. That could also prove to be interesting to have those statistics. So I think I'm about on time, so time for a few questions if you have. Yes?
It occurred to me that it would be useful and probably easy to include in the display the 4 current user IDs, and that way when you're looking at a search path like $user, you know who that's talking about.
Good idea. Yeah. Yes?
If I have root access in my Docker container, but not on the host platform, installed as a container, like Postgres in the container.
I can't really answer that. I mean, it's supported in PGTracer to trace what's happening in a container from outside the container. That's the whole namespace translation and translating the PIDs and things like that. This is handled, but running directly inside the container, I'm not sure how that.
I believe there's some setting you have to set the Docker that allows sublevel access. Where you need elevated privileges on the I think you may, because there's, like, I assume that it is similar to when I've done GDE on the Docker container. You have to, like, on the host, you have to have elevated privileges to be able to grant access to Docker to facilities that you need. That's a little different than this, but I assume it's similar.
One thing that could be a problem would be to have exactly the kernel header from your host version inside your container, because the EBPF code is generated and compiled when you run the tool. So as such, it needs access to the Linux headers for your specific kernel version. And so getting that exact version inside the container is maybe, I don't think, you can probably do this, but maybe it's not as easy as it sounds, because if you're running a container with some specific, using Alpine or something like that, how do you install the headers of the Linux kernel provided by your host Ubuntu, for example? So that may be a bit of a complication, but yeah. Yes?
Maybe you know the answer to this, maybe not, but given your work at Haven, even though on the open source team, do you see a path forward where Haven customers could actually end up being able to use this, so that there is a way to safely expose this to end users without compromising the cloud provider?
Well, without getting in specifics, I think it can safely expose by having the PGTracer collector running, gathering information, and then sending that back to a web interface or something. And just having a monitoring daemon, which will run, and maybe that can be triggered with a specific call by telling, well, I know I want to trace every single backend, or I want to trace a single one. I don't really see why this couldn't be integrated in a wider system. And actually, it might even be easier for someone like us to do this, because we have full control over the whole environment, and it's probably easier than if you deploy this yourself, to give someone access to SSH into the box and run the thing, and there's quite a lot of automation needed to deploy it safely, I guess, which is probably better suited to cloud operators.
But you don't have that today, right? Like, I have a customer, I can't actually make use of it.
Not right now, no. Okay, thank you.